The original Crash game was linear in progression. Completion of one level would lead you to the next. This is a process that the player would repeat until reaching the final boss of the game, Cortex. The formula changed for Crash 2 and Crash 3. Players would now be presented with a warp room, each containing 5 levels, and a boss battle. The boss battle could only be unlocked by completing each of the 5 levels and collecting the crystal inside. Things open up even more in the post-game of Crash Bandicoot 3. A secret warp room is available to players, and the levels are unlocked by collecting the relics from previous levels. The first of these levels only requires 5 relics to unlock. The player therefore is spoiled for choice as they can choose from any of the 25 original levels. Now, one of the new things introduced in the Insane trilogy is Coco's time machine. This allows Coco to travel back in time to the previous games and help Crash out. One thing she seems to be unable to do, however, is take relics from previous games back into the world of Crash 3 and use them to unlock the levels in the secret warp room. One reason why the relics might not be brought across is because Coco simply knows that only the relics within the world of Crash Bandicoot 3 can be used to unlock the levels within the secret warp room. How does Coco know this is the case, you may ask? Well, it could simply be that Aku Aku gives her a magical sounding answer. However, we can look to mathematics for a more scientific explanation. In order to build up this theory, we're going to use two key concepts, the first of which being polynomials. Now, because of their prevalence in countless areas of maths, polynomials have a lot of things that can be said about them, but for the purpose of this problem, we only need to consider the basics. Probably the simplest form of the polynomial is given here. As you can see, it's of the form a plus bx plus cx squared plus dx cubed, and continues on what is hopefully a straightforward pattern, and stops when we need it to. As you can see here, our variable x appears in lots of different forms within the polynomial. These different forms are what are known as monomials. As for our remaining letters that appear in front of our monomials, these are known as coefficients. Now, coefficients can be of many different types, but for the purpose of this video, all of our coefficients will be considered to be integers. To make use of our polynomials, we need to be able to evaluate them. So let's start off with a simple example. Consider the polynomial 3x squared plus 4x plus 1, and suppose we want to evaluate it at the value 2. Plugging 2 into our formula, we now have the calculation 3 times 2 squared plus 4 times 2 plus 1, which gives us 21. The second concept we're going to utilise is modular arithmetic. Now, much like polynomials, this is a topic we could talk for days about. However, instead of getting bogged down in too much detail, let's have Crash demonstrated instead. Now, I've positioned Crash in front of the giant screen, and for reasons that will become clear soon, I'm going to call this Warp Room 0. Presumably we all remember how we very first learned to count at school, using a number line. So, can we use the warp rooms in a similar way? Let's have Crash walk around and see what happens. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Hopefully you can see here what the problem is. We haven't actually arrived at warp room 13. What's actually happened is Crash has arrived at warp room 1 for the third time. This is essentially the basics of modular arithmetic. Instead of counting numbers that continue to get bigger, at some point we wrap around and go back to 0 and start again. We would now say that our calculations are being performed mod 6. Operations such as multiplication and addition are carried out in pretty much the same way, only now it's the case that their values must lie between 0 and 5. As an example, let's have Crash stand outside of warp room 3, and suppose we want to perform the operation 3 plus 4 modulo 6. All we need to do is simply have Crash walk around 4 spaces to the right. So he moves to warp room 4, 5, 0, and our answer is 1. Now back to our original problem. The first level in the secret warp room requires at least 5 relics from the other warp rooms to unlock it. Let's assume the reason that 5 or more relics is needed is because between them they have access to some kind of secret message or code that allows them to open the level. Wanting to make it so that any 5 of these 25 relics is able to crack the code makes this what is known as a 5-25 threshold scheme. To begin setting up our scheme, we first need to choose a value to use as our modulo. Now, any number greater than 25, so long as it is a prime, will suffice. However, in reality, you'd probably use a number that is hundreds of digits long, but for the case of example here, we'll just use the number 37. Our next step is to choose a secret message, a number that lies between 0 and 36. Hopefully here you can see the problem with using such a low number as 37. Someone that was potentially trying to break into the warp room without the appropriate relics could simply just go through and guess the individual numbers 0 to 36, and it wouldn't take them very long, which is why in reality you would choose a very large number. The next stage now is to choose a polynomial that will be used to hide our secret message m. The highest power of x in our polynomial is chosen to be 1 less than the minimum number of relics needed to get into the level. Since in our particular example that we're covering here requires 5 relics, the highest power in our polynomials will be 4. Remember that our polynomial looks like this. So now we need to choose values for the letters A, B, C, D and M, and these values will come from 0 to 36. For our example, let's go with the values A equals 4, B equals 7, C equals 23, D equals 17, and our secret message M will be 31. The level now has everything it needs to hide its secret message and can begin to start passing out bits of information to the 25 relics. The information each relic will receive is the polynomial evaluated at a different value, at which point the values for A, B, C, D and M are thrown away by the level so that no one else can use this information. We now have it set up so that 5 or more relics from any of the 25 levels will unlock the secret level, and the information can't be gathered from anywhere else, such as the other Crash games relics. Now let's imagine we're at the point in the game where Crash actually wants to unlock the first level in the secret warp room. He knows that he needs to recreate a polynomial that was used to hide the message in the first place, so he goes into the level's Toad Village, where he learns an input of 1 give an output of 8, Tomb Time, where he learns that the input of 2 give an output of 18, Dynamite that took 3 as an input and output 25, Double Header took a 4 and gave a 15, and Bye Bye Blimps took a 5 and output 33. Because he's been told by the level that he needs 5 relics, he knows that the general form of the polynomial is as such, so it's up to him now to figure out what the letters are. Again, because this is quite a small example, trial and error will get him there eventually, but for larger examples, or just a more systematic approach to solving this particular problem, you would use something known as Gaussian elimination. Without going into too much detail here, you can see how Gaussian elimination works. At each stage, a new letter has its value revealed, before finally reaching the end where it's revealed that M is equal to 31. But let's now suppose that Crash was only able to get 4 of the relics. Maybe one of the levels was too hard for him. What would happen when he went to the secret warp room and tried to unlock the level using only 4 pieces of information? Well, if we run our Gaussian elimination process again, we see that we finish one line earlier than before and are left with an equation like this. 12D plus 25M is equal to 17 modulo 37. This equation has multiple solutions, each of which has a different value for M. The problem is that it isn't clear which value for M is the right one here. Once again, it should be said that Crash could simply try every solution here because the values aren't very big, but in reality these values would be hundreds of digits long and it would take literally centuries of years for him to try every possible answer. The other issue we were concerned with was what if Coco went back in time to one of the old Crash games, collected one of the relics there, and tried to use that to unlock the secret levels in Crash 3. It might still be the case that this relic has 2 pieces of information on it, one that appears to have come from an input and one that appears to come from an output. There's no way those 2 values came from our secret polynomial though, because that was destroyed as soon as our 25 levels had received their information. Let's try our Gaussian elimination method one last time, but instead of using our normal last equation, we'll instead use 2 randomly chosen numbers, and these will represent the numbers that may have appeared on the relic that came from an earlier Crash game. If we choose 6 and 12, we see that it's business as normal when running through the process, and we even get a candidate value for the choice of M. The value here, however, turns out to be 19, so our secret level hasn't been tricked by an outsider relic. So there we have it, a possible explanation as to how the relics unlock secret levels within Crash 3, and another explanation as to why Coco can't simply bring relics across from other games. So what do you think? Are there any other sciencey explanations as to why the relics work in this way? Please feel free to discuss in the comments below, and thank you for watching.